Welcome to this lecture series in real analysis. In this lecture, we look at a very nice notion of subsequential limits and connect it with the notions of lim sub and lim inf and of course convergence. So all we need to know is the basics, what is a convergent sequence, etc. And most importantly, we need to know what is meant by the limit inferior and the limit superior of a real sequence. So let's recall, if we are given a real sequence xn, the limit inferior, written this way, lim inf of xn, is the limit of the inferiors. It's essentially, or what should I say? It is equal to, first you make this sequence, you take the infimum beyond a certain point. So this could be minus infinite, plus infinite, or whatever, or a real number, that's okay. But the key thing to note is that this is an increasing sequence in the extended reals. Extended reals are these things. Anything in this is called an extended real. So you just have the set of real numbers, you append them with these two new symbols and with the obvious inequalities. Fine, so once we are given a real sequence, we can create a new sequence. For each n, we get a new sequence, but this sequence lives here, and now you can take its limit. Because it is an increasing sequence, this makes sense in the extended reals. So this thing that we will get will live here. And this is called the limit inferior of xn. Similarly, we have the notion of limit superior, which is this thing. Okay, we saw this. And what have I written? Okay, and let us move on. Let's not spend more time here. Here are some problems for practice. These are very, very important to get down to the bones, what is, how to play with the notions of limit inferior and limit superior, and also about generally how to deal with questions of this sort. Like in analysis, we have inequalities. Inequalities are the defining features of analysis. So one should be very, very comfortable proving such things. All right. So here is the main notion or main concept of this lecture. So fix a real sequence, call it xn. We say that a real number a is a subsequential limit of the given sequence if there is a, this a and a can be confusing. Let me maybe call it S. So we say S in R is a subsequential limit of the given sequence if there is a subsequence of the given sequence which converges to S. Very natural definition. So the name has been aptly chosen. We say a real number is a subsequential limit if it is the limit of a subsequence. All right, fine, nothing very deep going on. So here is an example. Consider this sequence. What are all the subsequential limits? So this sequence is our favorite -1 + 1 -1 + 1, that thing. And you can easily show that the subsequential limits are precisely -1 and +1. So clearly you can find a subsequence which converges to -1 and you can find a subsequence which converges to +1, but you cannot find any subsequence which converges to anything else. And that is an exercise. It's a very, very simple exercise. Okay. And here is a simple note that if you have a convergent sequence, then what are all the subsequential limits? There is only one subsequential limit, which is nothing but the limit of the sequence. right? Again, that is very simple, because if a sequence converges, then every subsequence also converges and to the same limit. That's all. Immediate from that. Okay. So now we will, there is a not big, but there is a ultimate theorem that we want to prove, and towards that we will first prove two different lemmas. This is the first of the lemmas. So fix a bounded sequence of reals, start with a bounded sequence of reals. Then for each epsilon greater than 0, we have xn is less than that ultimately, and a counterpart. So we will just prove the first part, and the second part will be an exercise. Okay. So note that. This is very simple, and you should take this as an exercise before we look at what I'm going to show. But anyway, so clearly we have this. This is for all n. There is no ultimately here. That's clear. And the second one, what I'm going to write is the following, that this thing is less than lim sub plus epsilon ultimately. Now, why is this? Well, this is nothing. This is simply from the fact that from the definition of the limit superior, because the definition of the limit superior is that the limit of this guy is the limit superior, and immediately from that we get this inequality, right? So all I'm saying is that if yn converges to y, then yn is less than y plus epsilon ultimately. This is a one-way implication, but it is true. So you combine these two inequalities. One happens for all, the other happens ultimately, and therefore both happen ultimately. If both happen ultimately, both happen simultaneously ultimately, so you get that xn is less than equal to this thing. Why? Because just use the transitivity of inequalities. Xn is less than that, and that is less than that. So xn is less than that ultimately. And that's what we have written over here. Similarly, we have the second part, which is an exercise. Okay, very nice. So the second lemma says that it's kind of the other direction of the previous one. Fix a bounded real sequence, and for each epsilon greater than 0, we have this inequality, which is lim sub minus epsilon is less than xn frequently, not ultimately, but frequently, and the counterpart of lim inf. Okay, so let's see why. Again, you can take this as an exercise. So let's first write, for simplicity of notation, let's write a as lim inf and b as lim sub. Okay, so note that lim sub minus epsilon I should justify this. So what I'm saying is that suppose not. So let's go by contradiction. So suppose 1 is false, let's call this 1 and this 2, and we are only proving 1. So suppose 1 is false, then we must have b minus epsilon is greater than equal to xn ultimately. Alright? Why? Because if this does not happen frequently, then this must happen ultimately. That's all that we have written here. And now this is some fixed number which is dominating a sequence ultimately. Therefore, we also have this ultimately. Right? So if this were dominating xn for each n exceeding capital N, then this would also happen for each n exceeding capital N. That's all that we are saying. So we have this, but at the same time, this implies that this dominates the limit of this guy. Since the limit exists, it's a bounded sequence, this dominates the limit, which is lim sup, which is b. So we get b minus epsilon dominates b strictly. This is a strict, b minus epsilon is at least b, which is a contradiction, because b minus epsilon cannot be at least b. Epsilon is positive. Okay, so what happened? We had this much, and then since this is a convergent sequence, why this is a convergent sequence? Because xn is a bounded sequence. If xn is a bounded sequence, this itself is a bounded decreasing sequence and hence convergent. So if this is dominated by b minus epsilon, the limit of this will also be dominated by b minus epsilon, and that's what we have done here. And therefore, we get b minus epsilon is at least b, which is a contradiction, and therefore one must hold. We assumed on the contrary that one is false and arrived at a contradiction, so one must be true, and same reasoning applies to the second one. So we have these two things in our pocket. And now for the main theorem. So the main theorem is, fix a bounded sequence of real numbers and let S be the set of all the subsequential limits. Collect all the subsequential limits, that's a set. Then all we are saying is that the limit inferior is in S, the limit superior is in S, which we have written in this somewhat convoluted way, and that every subsequential limit is between the limit inferior and limit superior. Okay, so the limit inferior and the limit superiors are subsequential limits, and every subsequential limit is between the two. Okay, so this part is actually very easy. This is an exercise. We will justify this part, and in fact we will just justify that this is here because the argument for the limit inferior is analogous. Okay, so let b be equal to the limit superior, and now we know that for all epsilon greater than 0, we have xn is less than b plus epsilon and xn is greater than b minus epsilon frequently. So this happens because of lemma 1, and this happens because of lemma 2. In fact, in lemma 1, this was happening ultimately, but if something happens ultimately, it also happens frequently. But okay, in fact, I should have said something else. This happens ultimately, and this happens frequently. Therefore, this happens frequently. That's what I should have said. Okay, so this whole thing happens frequently, and therefore you can extract a subsequence which converges to B. This happens frequently for each epsilon, right? So therefore, B is in the set of all the subsequential limits. So yeah, this part maybe, we haven't proved it as a lemma or anything, but it's very simple. If for each epsilon you can find, or okay, let's look at it this way. So fix an epsilon, then you can, because of this statement, you can find some n which satisfies this. Now choose a smaller epsilon, let's say half of the previous one. Then you again find an n bigger than the previous n which satisfies this. And that way you can extract a subsequence. You just keep going, you extract a subsequence which comes closer and closer to point B. So if that didn't make sense, just take it as an exercise. This statement that for all epsilon greater than 0, this happens frequently implies that there is a subsequence of xn which converges to B. and that gives us that B is a subsequential limit, and hence lim sup is a subsequential limit. Similarly, lim inf is a subsequential limit, and this inclusion is an exercise. Fine, so we have proven this theorem, and let's look at a corollary which we had proven earlier. So if we have a bounded real sequence, and if you assume that there is some real number x such that whenever a subsequence converges, it converges to x, then the sequence, the original sequence itself converges, and it converges to x. So this is what we looked at earlier. We proved it using Cauchy sequences, but using the previous theorem, it is just one line. Because what does this say? This just says that the only subsequential limit is x. If the only subsequential limit is x, then lim inf and lim sup must be equal and should be equal to x by the previous lemma. But if the lim sup and lim inf are equal and equal to x, then the limit of the sequence exists. I mean, the sequence is convergent and the limit is x. So we saw in the previous lecture is that if lim inf equals to lim sup, then the sequence converges. We are talking about a bounded sequence. And further, the converse is also true. If the sequence is convergent, then this happens. So this was a reformulation of convergence. All right. So these things are very useful. And let us stop here. I'll see you next time.